Section 6.4 is work. Fun, huh? The term work is used in everyday language to mean the total amount of effort required to perform a task. As they say, it can be described using the push or pull of an object. For example, pushing a book across the table or the pull of the Earth's gravity on a ball. So in general, if an object moves along a straight line with position function S of t, then the force F in the same direction is given by Newton's second law of motion is F equals ma, and that's the product of the mass and the acceleration a. Now this uses the metric system, and so the mass is in kilograms, the displacement is in meters, the time is in seconds, and the force is in newtons. So we have all of these important things in your formula up here. So when you have the force of 1 Newton acting on 1 kilogram, it produces an acceleration of 1 meter per second. We use force to represent this, and that's customary in the U.S. In the case of a constant acceleration, so if our acceleration is constant right here, the force F is also a constant, and the work done is the product of the force and the distance. So you can see that happening. If F is measured in newtons, which we just discovered up there, and D is in meters, then the unit W is a Newton meter, which is called a joule J. If F is measured in pounds and D is in feet, then the unit for W is a foot-pound. So if you're working in the metric system, your answer will be in joules. And if you're working in the English system, the U.S. system, then your units will be foot-pound. These formulas right here, F equals ma and W equals FD, those are your important formulas for this section. So look at example 1. It says how much work is done in lifting a 1.2 kilogram book off the floor to put it on a desk that is 0.7 meters high. Use the fact that the acceleration due to gravity is g equals 9.8 meters per second squared. So we use the formula force equals mass times acceleration. But in this case, they tell us the acceleration is due to the gravity of 9.8 meters per second squared. So let's go ahead and fill that in. So we have the mass is 1.2 kilograms. And the gravity or acceleration is 9.8. My point won't work. 9.8 meters per second squared. So when we multiply these, we get 11.76. And if you think about the kilograms and meters and seconds squared, then we are in newtons. That's what's needed. So go back to the problem. It doesn't ask for the force. It says how much work is done. So remember that work equals the force times the distance moved. That's why we started with the force. So now we're going to say work equals force times distance. And we know that the force is 11.76 newtons. And the distance is 0.7 meters high. So when we multiply these, we get 8.2, and we are in newtons and meters, so this will be joules. And that's the answer to part A. So now let's look at part B. And do it right here. It's not a hard problem. Part B, it says how much work is done in lifting a 20-pound weight 6 feet off the ground. Okay, so when you look at this, we're given a 20-pound weight. So that's a weight, that's a force. A 1.2 kilogram, this is a mass, and the 20-pound weight makes it a force. So we can go straight to work equals force times distance. So our force is 20 pounds, and our distance is 6 feet. That makes it really easy, because we have 120. And notice we have pounds and feet, so this is actually foot-pounds. So if you pay attention to your labels, it's going to help you there. All right, so look at this next part. Now, when we start this, it says equation 2. And equation 2 is work equals force times distance. So it defines work as long as the force is constant. But if the force is not constant, you have to consider what happens then. So suppose the object moves along the x-axis in the positive direction from A to B, and to each point in between, the force acts on the object by f of x. So you can tell where we're getting into the calculus, where f is a continuous function. You have to have a continuous function or you have to deal with that, and we're not at that point. We divide the interval A to B into n subintervals with endpoints and equal width delta x. We use the sample point x sub I star in the ith subinterval, so that means we can pick any x in the interval, and that force is x sub I star. So do you see how this is very much like what we did before? So we have all of these, the work for each place is f of x sub I times the delta x, which is your change in x. And then it becomes a summation, and that moves us down into the integral. So what we come up with here is that work equals the integration from A to B of f of x dx. And that's based on the basis for your definition of an integral, as well as the summation notation that moves into the integrals. So this is the work done in moving an object from A to B. So that's what you're going to recognize here. One more thing you need here is that the f of x is the force. So this is the work to move an object from A to B when you have an equation for your force. So if we look at example 2, it says when a particle is located a distance x feet from the origin, a force of x squared plus 2x pounds acts on it. How much work is done in moving it from x equals 1 to x equals 3? So we know this is a parabola. We can see it. So we know that work equals the integration from A to B, f of x dx. So in this case, work equals the integration, and we're going from x equals 1 to x equals 3. And our equation is x squared plus 2x. That's the force with respect to x. So this is a nice, easy integration. We have x squared. The integration becomes 1/3 x to the third. The integration of 2x becomes x squared, and 2 over 2 is 1, from 1 to 3. So 3 to the third is 27, divided by 3 is 9, plus 9, minus 1/3, plus 1. So I have 18 minus 1 and 1/3. I know, mixed numbers, but sometimes they're easier to see. 18 minus 1 is 17, and then you got to take away the other third, and you have 16 and 2/3, which is the same thing as 50 over 3 if you get common denominators. And that's the answer. 50 over 3 is, we need to go back for a label. Here we have pounds, and we're moving it in x feet. So we have foot-pounds. Make sure that you get your correct label, especially as many of you are planning to be engineers. I know, what does that sentence mean? Math people don't care as much about labels. Any science teacher can tell you that. So I have to be careful to remember that you need labels. Okay, let's look at the next example. In the next example, we're going to use a law from physics. So Hooke's law is the law used here, and you can see your book says that it states the force required to maintain a spring stretched x units beyond its natural length is proportional to x. So if you look carefully here, you see your direct proportionality, y equals kx, that you learned in pre-calc. So k is a positive constant called the spring constant, and you can see it figured here. And then Hooke's law holds provided that x is not too large. So you're starting from your natural positioning of the spring, and then you're stretching it out farther. So a spring naturally sits all coiled up, and then you pull it out. that's what we're looking at, the force required to pull it or to stretch it X units beyond its natural position. So that's important to understand. So example 3 pulls this Hooke's law into the equation. Before we continue, notice that F equals kx, and we're talking about the force needed. If you think back to the beginning, our force is measured in newtons and our distance is in meters, so that means that our work is a newton meter, which is a joule. Or our force is measured in pounds and our distance is measured in feet, and so our work is measured in foot-pounds. So you're either going to use meters or feet when you're looking at distances, and that's important because sometimes they'll give you inches and you need to change it to feet, or they'll give you centimeters, or probably centimeters, because you don't pull a spring very far and you have to change it to meters. So if that's something you need to go back and look up before we get into it, you should probably do that. That's the prereq knowledge that some people forget. Going from centimeters to meters is just a change, and there are 12 inches in a foot. So there are 12 inches in a foot. I don't think either one is very hard. Sorry, meters to centimeters is just a decimal change. I left off a word there. All right, let's look at example 3. A force of 40 newtons is required to hold a spring that has been stretched from its natural length of 10 centimeters to a length of 15 centimeters. How much work is done in stretching the spring from 15 centimeters to 18 centimeters? Right away, do you see this problem of centimeters? So 10 centimeters to 15 centimeters, that means that we have, when 10 centimeters equals 0.1 meters. Are you thinking King Henry? A lot of people do their decimal exchanges by King Henry died Monday drinking chocolate milk, or died some word there. So you can always look it up, but you move your decimal point. For centimeters, you move your decimal point wrong button. You move your decimal point 2 places to the left to change it to meters. So then we have 15 centimeters. So this is 0.15 meters. Pay attention to the fact that we have 15 and 10 really. And then the next set, we're starting at 15 centimeters, which is 0.15 meters. And we're moving it to 18 centimeters, which is 0.18 meters. So Hooke's law tells us that f of x equals k, or a spring of constant x. And that's the force required to stretch my spring x units beyond its natural length. So if you think about this, we have the force is 40 newtons from up here, and its natural length is 10. This is important. Its natural length is 10 centimeters, and we're stretching it to a length of 15 centimeters. So this directional proportionality is similar to pre-calc, that you're going to have to do it twice. You've got to find your constant of proportionality before you can use it. So we're going to say 40 equals, and K is what we're looking for, 40 newtons. Keep that in mind. K is what we're looking for, and X is how far we stretched it, the distance. So if you look back here, we stretched it 0.05 meters. So solving for K is easy. We're going to divide by 0.05 on both sides. So K equals 40 divided by 0.05 is 800. 800. And then we go back to the fact that we were looking for f of x, not just K. So f of x equals 800x. Now you can see that sets up nicely for our work integration. So we're going to say work is the integration of 800x dx. Now let's talk about bounds. Some people want to throw in the 15 and the 18 centimeters and just put 0.15 and 0.18. But you have to think about the fact that what we're doing is we're stretching the spring. We're not just pulling it the whole 0.15 meters. We started out at 10 centimeters, so we're not pulling it the whole 15 centimeters, we're only pulling it 5. So our lower bound is 0.05. I struggle with decimals on this system. and our upper bound is 0.08. Make sure you know that's an O and not a 1. So hopefully the bounds make sense. We're pulling it from 0.1 to 0.15 and 0.18. So now we can integrate. 800x is easy to integrate. It becomes x squared, so we divide that by 2 and we get 400x squared from 0.05 to 0.08. So that means I've got 400 times 0.08 squared. 0.08 squared is 0.6. Let's say 0.08 squared because that's 0.0064 minus 400 times 0.05 squared. So when you do that all out, you get 1.56 joules. Okay, look at number 9. I think it's just something you need to see before you have to go do it. And it says, suppose 2 joules of work is needed to stretch a spring from its natural length of 30 centimeters to a length of 42 centimeters. Notice they give you the work right here. They give you the work, and then the natural length is 30 centimeters. So when you start off with f of x equals kx, because we're stretching a spring, so we're using Hooke's law. We're going to use that to say work equals the integration from a to b of kx dx. Now the work is 2 joules, and our natural length is 30 centimeters, which is 0.3, and we're starting there. So we're starting at 0 and stretching at 0.12 meters, because 42 centimeters is 12 centimeters away, which is 0.2 meters. And then we have kx dx. So we have 2 equals, this is an easy integration. I have 1/2 kx squared from 0 to 0.12. So 2 equals 1/2 k. I would move that 1/2 over and make it a 4 and just work with kx squared. But that's okay. K, and then I have 0.12 squared minus, and 0 times anything is 0. So we have 2 equals 1/2 k 0.0144. Can you do the math to get there? I'm sure that you can. So k equals 277.78. And the label here, because it's force equals mass times gravity, so the label here is newtons over meters. So now we're going to do the second part of this, part A actually. Now that we found that, we're going to say f of x equals, I have my eraser on, oops, f of x equals 277.78 x. So part A says how much work is needed to stretch the spring from 35 centimeters to 40 centimeters. Well, the natural length is 30, so 35 is 5 centimeters away, that's 0.05, to 40 centimeters is 0.10, and our equation is 277.78x dx. So when we integrate this, we're going to divide by 2, so we have 138.89x squared from 0.05 to 0.10. So we have 138.89 times 0.10 squared. I know you can put 0.1, but it helps me, I don't know. 138.89 times 0.05 squared. Notice I don't have big brackets and everything. There's nothing being multiplied. There's only one term per, there's only one thing happening per each set. It's like when I multiply by 10, there's a monomial there and there's a monomial there. So you don't have to have the parentheses. When you do this, it comes out to 1.041675. So we're going to write 1.04 joules. I like 2 decimal places. When you're working for me on paper, 2 decimal places are always acceptable. So let's look at part B. But you have to keep this in mind. Part B is actually not very long. I think I'll erase all this work over here and do it in this side. So part B says, how far beyond its natural length will a force of 30 newtons keep the spring stretched? So here's our force equation right here. And we know that the force is 30. So we're going to say 30 equals 277.78x. And x is how far we stretch it beyond its natural length. So that's exactly what we're looking for. So we're going to take 30 and divide it by 277.78. And we get 0.10799, whatever. So this is 0.11 meters, which equals x. And everything is in centimeters. So WebAssign probably wants you to say 11 centimeters. Again, I'm happy with 2 decimal places. Make sure you know how many decimal places WebAssign is asking for. If you have any questions, let me know. Thank you.